Chapter 1, Section 3, Atomic Processes. In the previous chapter, Feynman described how we could understand the states of matter better by understanding that matter was made of atoms. In this chapter, he extends that view and says that it's not only that we can explain how things are by thinking of them as atoms, but that what we can do is we can describe and understand how they behave. You see, when something changes, when, for example, Feynman talks about water, and in the previous example he spoke about how water, in its various different states, could be explained using atoms. Well, in this section, he talks about changes that might occur to water, and how those changes themselves can be understood by considering that matter is made of atoms. So here I have some salt, sodium chloride, and I'm just going to put a little bit in the water. I'll give it a little stir, and what you can see is, apart from some of the larger crystals, it's disappeared. It's dissolved. Now, dissolving as a process is a change. There was liquid water before, and there was solid salt crystals. Now afterwards, well, we have a solution of, salt water. So this change we describe as a process. Something has happened. And the processes that we observe in science are better understood if we consider what's happening at an atomic scale. Feynman asks us to consider what happens at the surface of water and air. And he gets us to imagine this diagram here, where we have water at the bottom and air at the top. And he describes that there in the air we have oxygen molecules, nitrogen molecules, and some water vapour. Now, it is also the case that down here amongst the liquid water, and you can see the molecules are closer together, that there are some dissolved air molecules here, some nitrogen that has got lost in the liquid water. Now, this process, the process of the water molecules down here having some thermal energy, would be visible in the motion of those particles. They would be jiggling around, colliding with each other. Now, some of them, depending on the nature of those impacts, might be collided with, and a small amount of energy might exchange. No big deal. But just occasionally, and this would happen right here on the surface of water like this, that a chance collision could occur that would result in one of these surface water molecules breaking free and becoming one out in the air and becoming a molecule of water vapour. Now, this process is called evaporation, and we see it in any body of water that's just left open to the air for a good deal of time. Now, what Feynman asks us to consider is what happens if we put the lid on. Then what we get, and his words are, a dynamic and interesting phenomenon. That even though the lid is on, this water is now going to stay in here forever, or until I take the lid off. Because what's going to happen is that with the lid on, every now and again a water molecule will break out of the surface and enter the gaseous phase. But what will also be going on is that some of the water molecules in the gaseous phase will come down and land in the water again, and so this will occur in equal number. As many that are evaporating will also come back down and return to the water. And so the total amount of liquid water in here will stay the same. You won't find, if I leave this 3 weeks and come back, that half of it has turned to water vapour, because the process of evaporating is happening at the same rate as the process of the water vapour coming back down and turning back into liquid. Of course, what will happen if I take the lid off is now this area above the water will become enriched with water vapour, and it would be in fact heavier with water vapour than the air around us. With the lid off, what's going to happen is that some of the water vapour in here is going to spread into the rest of the room, and it's going to continually make the air above the water essentially lower in concentration of water vapour than it would be if I put the lid on, which means that the process of liquid water turning into water vapour is going to be able to occur at a greater rate than the water vapour in the air turning back to liquid. And it's not because the evaporation is happening more with the lid off, it's because there's less water in the air that can restore the equilibrium if now, rather than the lid on, we're exposed to the dry, larger body of air that is the room. So Feynman talks about this process, and he talks about it in terms of the evaporation that occurs when you're sweating, when you get quite hot and you're doing some exercise, and your sweat glands produce a liquid on the surface of your skin. Now what I have here is, I'm not going to start doing any exercise, but I'm going to demonstrate with a different fluid here. This fluid is ambient temperature. It's the same temperature as the rest of the room. And what I'm going to do is I'm just going to pour a little on my hand like this. And I'm just going to leave it. And then what I want you to do is just to look at my hand, and where I have poured it, you can see there is the darker mark where it is definitely cooler. So what is going on? What is occurring here that means my hand is cold where I have poured some liquid on it that is room temperature? Why has the presence of the liquid made my hand go cold? Well, it's all to do with that process of evaporation. You see, what we said was that sometimes a particle might be bumped, given more energy than usual, and that this would be enough to let it leave the surface. If you now think of where the energy is, there is a whole chunk of energy, thermal energy, that particle has taken away. And so what remains, the liquid left over, and I can now feel that it is really cold on my hand, the liquid left over is now lower in thermal energy than it was before the evaporation took place. And this means that when I sweat, the particles moving faster carry away the thermal energy, leaving only those particles that have less thermal energy behind. So it's cooler behind. So what happens when we consider the canister with the lid on? Because evaporation is going to be occurring in here, and we said that it's always occurring, and so you would imagine that would the temperature change? Well, every time particles do leave the surface, then we find that we have some of the thermal energy removed. It is transferred away. But what we said with the lid on was that particles were returning to the water at the same rate that they were leaving. And when they return to the water, they bring that thermal energy back again, because whatever thermal energy they have when they turn into a gas is just their kinetic energy as they move around, and as they re-enter the water, they've brought it all back again. That's why the water with the lid on stays at constant temperature, because every time thermal energy is taken away, it is being brought back at exactly the same rate. And if we looked at it with this, we would not find that it changes temperature at all, not by that mechanism anyway. Ooh. Have you ever wondered why blowing on a cup of coffee helps it cool down? It's a strange one, really. Well, it's to do with this process. You see, what's going to happen is that the more energetic particles are turning into water vapour immediately above the actual coffee itself. Now, whilst they're there, some of them are going straight back into the coffee, and so therefore there's no net change of temperature. Now what you can do is you can blow away the air that is saturated with those high energy water molecules by just doing this. And now they've gone. And the air that's replaced it is very dry air without those high energy water molecules in at all. All you have to do to cool it down is to stop those high energy water vapour molecules from re-entering the liquid, and the easiest way to do that is just to blow them away. Now, this leads to the main mechanism why puddles dry up. You see, a puddle does not have to get to 100 degrees to disappear. I mean, it's not 100 degrees outside, and puddles do dry up. So what is causing that? Well, it's a combination of two things. Gentle energy input, perhaps from the sun, is one thing. But actually, the dominant mechanism that makes puddles dry up is the wind. Because what's happening above the puddle is the air is becoming saturated with water molecules, and the wind is just blowing them away. And now being taken away from the puddle, they can't re-enter the puddle, and it means that the puddle now has less water in it. This is why puddles dry up. It's because the wind is blowing away that saturated air. Have you ever left a glass of water on a bedside table and forgotten about it, and come back to it several days later and looked into it? What you might notice is that there's all these little tiny bubbles in there. Where have they come from? Well, Feynman gives us a good explanation for this, because he talks about this process of evaporation, of what the water molecules are doing as they enter the air, and how there is this two-way flow from the liquid to the air and from the air back into the liquid again. But what about the air itself? Well, it's possible that some of those molecules of air, the nitrogen molecules or the oxygen molecules, well, they could go down towards the surface and accidentally get buried amongst the liquid water molecules. This we would call dissolved air. Believe it or not, all fluid has got dissolved air within it. This fluid here has got dissolved air in it. And the best way of observing that is to leave it for a very long time. Because though that dissolved air could quite happily come to the top and leave, it's more likely to swirl around in there. And little tiny imperfections on the inside of the glass are going to be points of nucleation. Points where either the dissolved air or maybe a small pocket of water vapour can start to form. And as soon as you get a few of those molecules together, then that becomes a miniature surface where more and more of the particles that are dissolved of the air or of water vapour can enter into that bubble and slowly start to expand it. And so it grows with time. Now, certainly, we can see dissolved gases in liquids in other situations too. Now, what is quite common in the drinks industry is to create bubbly liquids. And the way that they do that is they take the liquid and they subject it to a high pressure atmosphere, in this particular case, carbon dioxide. So the liquid is there and there's carbon dioxide above it, and they put it under so much pressure that the carbon dioxide molecules get inside and dissolve into this liquid, and then the lid is put on. And that is why it is under pressure right now, and that is why there are not any bubbles appearing along the sides. But the second I release the pressure, then what we now find is the pressure is released, and now coming to the surface from the solution is that carbon dioxide that was dissolved in the first place. And that is how we get fizzy drinks. It's just a part of the process that Feynman describes in terms of the molecules of the atmosphere being dissolved in the liquid and the liquid evaporating up into the atmosphere. Take a look at this giant salt crystal. You see, Feynman, he doesn't just talk about atomic processes in terms of evaporation and condensation around the boundary of liquid. He also talks about other processes that we might see. And one of those involves salt. I'm going to just get a few grains just here. under the microscope. Let's have a little look. So here we can see, under the microscope, that the structure of a grain of salt is almost exactly the same as the structure of that large crystal. Here, under higher magnification, you can see the regular square shapes, and this is caused by the structure of this crystal at an atomic level. So if we were to look at the process of dissolving these salt crystals in some water, can understanding the atomic processes help us to better understand and explain why it's dissolved? Well, Feynman argues that we can, and he does so by talking about the salt crystal. Now, he points out that the salt crystal would look something like this. Not quite like this, but something like this. Whereas in a salt crystal, they're not all the same element, as you can see in this configuration. They alternate between being a sodium ion and a chlorine ion. And I've got a depiction of that just here on the board. And what you can see is the chlorine ions here are slightly negative, and they are attracted, when you put them in water, to the slightly positive hydrogen atoms in the water molecules. And the sodium ions are slightly positive, which means they're attracted to the negative of the oxygen atoms. It means that in the process of sticking salt in water, what you find is water starts to take the salt crystal apart. And what you can see here is a chlorine atom that has been removed, and you can see that it has now got all of the hydrogens of the surrounding water molecules facing towards it. Now, the attraction is so great between the hydrogens and the chlorine that the water molecules will work in between the cracks and gently cleave away atom by atom by atom. And this is the process of dissolving. And when the sodium and the chlorine is dissolved, the atoms are totally separate. You have chlorine ions in solution, and you have sodium ions in solution. Now, of course, as with the evaporation that we spoke about earlier, it was a two-way process, and it's possible for it to happen in two different directions. If I placed into a tank of water some salt, of course, it would start to dissolve. That is until the point where the water becomes saturated with the ions of this solid. When that happens, no more of these atoms can get in, because each one of the atoms is surrounded by water, but there's no more gaps, and that ends the process. But in a closed situation, what is going to be happening is you're going to have atoms going into solution and atoms coming out of solution. Now, it might well be that if these two are balanced, atoms coming into solution and atoms coming out of solution mean that the size of your salt crystal is going to stay constant. It's neither going to dissolve any more, nor is it going to get any bigger. And so this is a process that we can totally understand by picturing and modelling what is going on at an atomic scale. For both of these processes, they're two-way processes, evaporating into the air from a liquid and having those molecules condense back and rejoin that liquid again. And here, the dissolving of a solid into a liquid and having those atoms rejoin the solid again in the form of crystallization, two-way process. Now, a part of science is coming up with a model that allows you to make predictions. In both of these cases, you could ask, well, what would our model do if we changed something? What would happen if both of these were put under higher temperature? So both situations had more thermal energy. If this one had more thermal energy, then you could imagine that the collisions that would occur to give any one of these water molecules enough energy to escape would occur more regularly because more of the particles have the energy. And so what you would see is heating this one up would make the reaction happen more from left to right. You would get more evaporation and less condensation. And this is what actually happens. If you heat a pan of water, it will evaporate faster than an unheated pan of water. So our model enables us to validate the prediction that heating it up is going to increase the change of state this way. Now, what about what happens here? What happens if we change the temperature? Well, if we change the temperature, then the jiggling motion of all of these atoms is going to be greater. Now, we said that the mechanism by which one of these atoms is cleaved off is when the water starts to creep in behind it. Now, if there is more motion in the mix, then that is going to happen more. Also, the vibration of the lattice, if it is vibrating more, then it's momentarily going to open up gaps between the atoms that the water can get in between to start that cleaving process. So we'd expect, from our understanding of this model, that increasing the amount of thermal energy in the system should make this two-way process to be dominated towards the right-hand side, that there should be more dissolving than crystallization. And indeed, that is what happens. If I take some warm water and cold water and try to dissolve sugar in both, then the sugar dissolves much more rapidly in the warm water. And so there we have it. Feynman said the atomic hypothesis enables us to understand and make predictions in a really powerful way. And it's not just about the states of matter, it's also the processes that can be explained using the atomic hypothesis.